A yaw rotation is a movement around the yaw axis of a rigid body that changes the direction it is pointing, to the left or right of its direction of motion. The yaw rate or yaw velocity of a car, aircraft, projectile or other rigid body is the angular velocity of this rotation, or rate of change of the heading angle when the aircraft is horizontal. It is commonly measured in degrees per second or radians per second. Another important concept is the yaw moment, or yawing moment, which is the component of a torque about the yaw axis. Measurement. Yaw velocity can be measured by measuring the ground velocity at two geometrically separated points on the body, or by a gyroscope, or it can be synthesized from accelerometers and the like. It is the primary measure of how drivers sense a car's turning visually. It is important in electronic stabilized vehicles. The yaw rate is directly related to the lateral acceleration of the vehicle turning at constant speed around a constant radius, by the relationship, tangential speed yaw velocity equals lateral acceleration equals tangential speed 2/radius of turn. In appropriate units, the sign convention can be established by rigorous attention to coordinate systems. In a more general maneuver where the radius is varying, and/or the speed is varying, the above relationship no longer holds. Yaw rate control. The yaw rate can be measured with accelerometers in the vertical axis. Any device intended to measure the yaw rate is called a yaw rate sensor. Yaw rate control is a system that maintains the yaw rate of a vehicle, for example a car, according to the values requested by the driver. It differs from simple yaw control because is not the heading angle the controlled variable, but its variation rate instead. It is one of the main targets of electronic stability control systems. Arrows, darts, rockets and airships have tail surfaces to achieve stability. A road vehicle does not have elements specifically designed to maintain stability, but relies primarily on the distribution of mass. Road vehicles. Studying the stability of a road vehicle requires a reasonable approximation to the equations of motion. The diagram illustrates a four-wheel vehicle, in which the front axle is located a meters ahead of the center of gravity and the rear axle is b meters towards the rear from the center of gravity. The body of the car is pointing in a direction while it is traveling in a direction. In general, these are not the same. The tire treads at the region of contact point in the direction of travel, but the hubs are aligned with the vehicle body, with the steering held central. The tires distort as they rotate to accommodate this misalignment, and generate side forces as a consequence. From directional stability study, denoting the angular velocity, the equations of motion are: the coefficient of will be called the damping by analogy with a mass spring damper, which is a similar equation of motion. By the same analogy, the coefficient of will be called the stiffness, as its function is to return the system to zero deflection, in the same manner as a spring. The form of the solution depends only on the signs of the damping and stiffness terms. The four possible solution types are presented in the figure. The only satisfactory solution requires both stiffness and damping to be positive. If the center of gravity is ahead of the center of the wheelbase, this will always be positive, and the vehicle will be stable at all speeds. However, if it lies further aft, the term has the potential of becoming negative above a speed given by. Above this speed, the vehicle will be directionally unstable. Corrections for relative effect of front and rear tires and steering forces are available in the main article. Relationship with other rotation systems. These rotations are intrinsic rotations and the calculus behind them is similar to the Frenet-Serret formulas. Performing a rotation in an intrinsic reference frame is equivalent to multiply its characteristic matrix by the matrix of the rotation. History. The first aircraft to demonstrate active control about all three axes was the Wright brothers' 1902 glider. See also, adverse yaw, aircraft principal axis, Coriolis acceleration, directional stability, flight dynamics, 6 degrees of freedom, vehicle dynamics, yaw rate sensor, references, aircraft rotations. Retrieved August 4, 2008 A.